Have you ever been there? In the lab, you've made some stuff,
Yeah.
and you're just staring at the flask thinking, okay, great, but what is this?
Yeah.
Figuring out the exact molecular structure, I mean, that's a huge challenge in organic chemistry.
Oh, absolutely. For a long time, it was really painstaking work, often unreliable, too.
But then this incredible tool came along,
Yeah.
like the ultimate detective for molecules. And that's what we're diving into today, nuclear magnetic resonance spectroscopy, NMR. Think of it as maybe a shortcut to really knowing the building blocks of matter. We're digging into Chapter 19 of Organic Chemistry, I for Dummies, seconded, to really unpack how NMR works.
Right. Our mission today is, well, first, why is NMR so critical? How does it actually function, fundamentally? And then, the big one, how do you read an NMR spectrum? We'll break down things like chemical shift, integration, coupling, all these clues that tell you exactly how a molecule is put together. The goal is really to make these concepts, which can seem complex, feel clear and intuitive.
Okay, so let's set the scene. Before NMR, the book says it swaggered onto the scene, chemists were stuck with methods that were, and I quote, wearisome, unreliable, and about as fun as a root canal. Comparing physical properties, trying to make known derivatives, sounds tedious.
It really was. Weeks of work, sometimes hitting dead ends. But NMR just, well, it transformed everything. What took weeks could suddenly be done in minutes. You just, pop your sample in the machine, run the experiment quickly, print the data, boom.
How does that compare to other techniques like mass spec or IR?
Good question. Mass spec gives you the molecular weight, maybe some fragments. IR tells you about functional groups, what kinds of bonds are there. But NMR is the one that shows you the whole picture, how everything is connected, atom by atom. It's definitive.
The book uses this really powerful analogy comparing structured determination to chess.
Ah, yes.
It says NMR has the moves of the queen. It's the most powerful piece on the board.
That's a great way to put it, because it can really nail down the structure of almost any organic molecule. Simple ones, sure, but also incredibly complex things like huge enzymes.
So it's the ultimate molecular compass, basically. Tells you exactly what you've got. Okay, so how does this detective actually see inside a molecule? Let's get into the theory, but keep it, straightforward.
Okay, so fundamentally, NMR lets us see the nuclei in a molecule, specifically their chemical neighborhood. This tells us about the environment, the number of different kinds of nuclei, and that's how we piece together the structure. Now, a key point. Not all nuclei work for NMR. We can only see those with spin. Think of them as tiny spinning nuclear magnets.
Spin.
Yeah. Nuclei with odd atomic and mass numbers have this property, like hydrogen-1, that's proton NMR, the most common type, also carbon-13, nitrogen-15, fluorine-19. But nuclei with even atomic numbers, like the main isotopes of carbon, carbon-12, or oxygen-16, they don't have this spin. They're NMR inactive.
Okay, so only certain nuclei act like tiny magnets? What happens next?
Right. So you take these nuclei, these tiny magnets, and you put them in a really strong external magnetic field. Let's call it BO. And these nuclear magnets, they can align either with the external field that's a lower energy state, called alpha spin, or they can align against it, a higher energy state, beta spin.
Like tiny compass needles lining up, sort of.
Exactly. And there's an energy difference, delta E, between those two states. That energy difference is what the NMR experiment actually measures. And crucially, that energy gap changes depending on the strength of the big magnet, BO, and the specific chemical environment around each nucleus.
So how do you measure that energy gap?
That's where the resonance part comes in.
Yeah.
You irradiate the sample with radio waves.
Radio waves, like from the radio.
Sort of, yeah.
Yeah.
Specific frequencies. When the frequency of the radio wave exactly matches that energy difference, delta E, for a nucleus, the nucleus absorbs that energy, that light, and it flips its spin from the lower energy alpha state to the higher energy beta state.
That's the spin flip, and the absorption is the resonance.
Precisely. Nuclear magnetic resonance. The detector measures the frequency where this absorption happens and plots it. That's your NMR spectrum.
So high frequency absorption means a big energy gap. Low frequency means a small gap.
You got it. But think about it. If all hydrogens, say, felt exactly the same magnetic field, they'd all resonate at the same frequency. You'd just get one peak. Not very useful.
Right. So something must make them different.
Exactly. And that something is electrons.
Electrons. How do they get involved?
Well, electrons are moving charges too, right? So they create their own tiny magnetic fields. And these electron fields actually oppose the big external field BO. They effectively shield the nucleus from feeling the full strength of the magnet.
Ah, okay. So more electrons around a nucleus means more shielding.
Yes. Think of it like the nucleus is wearing an insulating jacket of electron density. It feels less of the external cold, the magnetic field.
So if a nucleus is shielded, jacked with electrons, it feels a weaker effective field.
Which means the energy gap between its spin states is smaller. So it takes low-frequency radio waves less energy to make it flip.
Okay, that makes sense. And the opposite, less shielding.
Right. If you have a hydrogen near something electronegative like fluorine, oxygen, nitrogen, those atoms pull electron density away.
So the hydrogen is deshielded.
Exactly. It feels more of the external magnetic field, though. The energy gap is larger, and it resonates at a higher frequency, higher energy needed to flip.
So the spectrum plots these different frequencies. But you said the frequency depends on the magnet size. How do we compare spectra from different machines?
That's a critical point. Standardization, we need a universal reference point, and that reference is usually tetramethylsilane, TMS.
TMS, why that specific molecule?
Well, TMS has hydrogens bonded to silicon. Silicon is less electronegative than carbon. It actually donates electron density. So the TMS hydrogens are highly shielded. They resonate at a very low frequency, lower than almost anything else you'll see in organic chemistry. So we just define the TMS signal as 0 parts per million, or ppm.
Ah, ppm. So everything else is measured relative to TMS.
Precisely. That relative frequency is called the chemical shift, symbol delta, measured in ppm. For proton NMR, the scale usually goes from 0 ppm, near TMS, up to maybe 15 ppm.
And low ppm means shielded, electron-rich. High ppm means deshielded, electron-poor.
You've got it. So chemical shift is your first big clue. It tells you about the electronic environment, what kind of functional groups might be nearby. 0 ppm is electron-rich. Up near 15 ppm is electron-poor.
Okay, chemical shift tells us about the environment. But how many peaks should we expect to see? That brings us to chemical equivalency and symmetry, right?
Exactly. The basic rule is simple. Every hydrogen in a unique chemical neighborhood shows up as its own peak. But, and this is key, hydrogens in identical chemical environments are called chemically equivalent, and they all show up together as a single peak.
Can you give an example?
Sure. Take methanol, CH3OH. It has 4 hydrogens, but you only see 2 peaks. Because the 3 hydrogens on the CH3 group are all identical. They're equivalent. So 1 peak for them. The OH hydrogen is in a different environment, so it gets its own separate peak. 2 peaks total.
Okay. What about something like butane, C4H10? That's 10 hydrogens.
Right, 10 hydrogens. But butane has symmetry. The 2 CH3 groups on the ends are equivalent to each other, and the 2 CH2 groups in the middle are also equivalent to each other.
So it's only 2 types of environment.
Exactly. So only 2 peaks in the 1H NMR spectrum, even though there are 10 hydrogens. It's really helpful to draw the molecule out, see the symmetry, see which hydrogens are identical.
Okay, so chemical shift is about electron density, especially near electronegative atoms pulling electrons away. But you mentioned something else affecting it, pi electrons.
Ah, yes. Diamagnetic anisotropy. Sounds complicated, but the idea is fairly straightforward.
Let's hope so.
Think about the pi electrons in something like a benzene ring. When you put that ring in the magnetic field, those pi electrons circulate. That circulation creates its own little induced magnetic field. Now here's the cool part. Outside the ring, where the hydrogens are, this induced field adds to the main external field bow.
So those hydrogens feel an even stronger field.
Right. Which means they get deshielded even more. They show up at much higher chemical shifts than you might expect, just based on electronegativity alone. Usually around 7-8 ppm for aromatic protons.
Does this happen with double and triple bonds too?
It does. Hydrogens on double bonds, alkenes, and triple bonds, alkyne, also experience similar effects from the pi electrons, shifting them to higher ppm values than simple alkane hydrogens.
And these effects add up, right? If a hydrogen is near an oxygen and part of a double bond.
Absolutely. The effects are cumulative. Multiple deshielding influences will push the chemical shift even higher. There are tables and charts that show typical ranges, which are really useful guides.
Okay, so chemical shift tells us where the peak is, giving clues about the environment. What else can NMR tell us? You mentioned 2 more things.
Yes. Integration and coupling. Hugely important.
Let's start with integration.
Okay, integration is simply the area underneath an NMR peak, and that area is directly proportional to the number of hydrogens that peak represents.
So a bigger peak means more hydrogens.
A peak with a larger area, yes. Sometimes spectra show an integration curve plotted over the peaks. The height of that curve step corresponds to the area. The crucial thing is it gives you the relative ratio of hydrogens, not the absolute number.
How does that work?
So if one integration curve is, say, 2 centimeters high and another is 1 centimeter high, it tells you there's a 2-to-1 ratio of hydrogens represented by those peaks. It could be 2 hydrogens and 1 hydrogen, or 4 and 2, or 6 and 3, just the ratio.
Okay, so integration, it'll relative number of hydrogens. Got it. Now, what about coupling? You said that tells us about neighbors.
Exactly. Coupling, or spin-spin splitting, is where a single peak gets split into multiple smaller peaks, like a multiplet.
Like in ethanol. You mentioned ethanol earlier. CH3CH2OH. 3 unique environments, right?
Right. A CH3 group, a CH2 group, and an OH group. The integration ratio is 3 to 2 to 1, but if you look closely, the CH3 signal isn't one peak, and neither is the CH2 signal. They're split.
What causes the splitting?
It's the magnetic influence of neighboring hydrogens. Specifically, hydrogens on adjacent carbons talk to each other through the bonds. Their little magnetic fields interact.
Adjacent carbons only.
Typically, yes. Significant coupling usually only happens between hydrogens separated by 2 or 3 bonds. And another key rule: chemically equivalent hydrogens don't couple with each other.
Okay, so how do we predict the splitting?
We use the n+1 rule. It's simple but powerful. A signal is split into n+1 peaks, where n is the number of equivalent neighboring hydrogens.
Let's try that on ethanol, the CH3 group. Its neighbor is the CH2 group.
Correct. The CH2 group has 2 equivalent hydrogens, so for the CH3 signal, nx2.
So n+1 is 2 + 1, it's 3. A triplet.
Exactly. The CH3 signal appears as a triplet. Now, what about the CH2 signal? Its neighbor is the CH3 group.
The CH3 group has 3 equivalent hydrogens, so n equals 3. n+1 is 3 + 1 = 4. A quartet.
Perfect. The CH2 signal is a quartet, and the OH hydrogen. It usually doesn't couple, as we'll discuss later, so it's just a single peak, a singlet.
Singlet, doublet, triplet, quartet. Those are the names for the patterns.
Yep, 1 peak is a singlet, 2 is a doublet, 3 a triplet, 4 a quartet, and so on.
Now, you mentioned the distance between those split peaks, the J value.
Yes, the coupling constant, or J value. It's measured in hertz. Hertz, not ppm. It's the distance between the individual lines within a multiplet.
Why is that important?
Because hydrogens that are coupled to each other will have the same J value. It's a crucial piece of evidence.
So in ethanol, the splitting distance in the CH3 triplet would be exactly the same number of hertz as the splitting distance in the CH2 quartet.
Precisely. That confirms they are neighbors talking to each other. Coupling is like the molecule's social network map. It tells you who is directly connected to whom.
Okay, the n+1 rule seems clear for simple cases like ethanol. But what if a hydrogen has neighbors that aren't equivalent to each other, like a CH group next to both a CH2 and a CH3?
Good question. That's where it gets a bit more complex. The simple n+1 rule doesn't quite cover it directly. When a hydrogen has 2 or more sets of non-equivalent neighbors, you essentially apply the n+1 rule for each set separately, and then the effects multiply.
Multiply. How does that work?
Okay, say you have a hydrogen, let's call it HX, next to a CH2 group, let's call them H's, and also next to a different single hydrogen, HB. First, HX couples with the 2 H's, N2, so n+1 = 3. That splits HX into a triplet. Then, each of those 3 triplet lines gets split again by the single HB neighbor. For HB and AJ, so n+1 = 2, it splits each line into a doublet.
So you get a triplet of doublets, or wait, 3 lines split into 2 each. That's 6 peaks total. 3 by 2 = 6.
Exactly. You multiply the multiplicities. It would technically be called a doublet of triplets if the J value for HB coupling is larger, or a triplet of doublets if the J value for hair coupling is larger. You usually name it starting with the larger splitting.
Wow, okay. Does it always look that complex?
In practice, sometimes coupling constants are very similar, so the peaks overlap, and you might see fewer lines than the maximum possible. As a quick approximation, you could just add up all the neighbors, equivalent or not. So in that example, 2 A's plus 1 HB equals 3 neighbors total. N+1 would be 4. So you might approximate it as a quartet, even though it's really 6 lines if the J values are different enough.
Is there a way to predict the exact pattern when the J values are different?
Yes. Chemists use something called a tree-splitting diagram.
A tree diagram.
Yeah. You start with the unsplit signal. Then you apply the splitting rule for the neighbor with the largest J value first, drawing the lines separated by that J value in hertz. Then you take each of those lines and split them according to the n+1 rule for the next neighbor, using its J value for the separation. You keep going for all sets of neighbors.
And the final lines on the diagram represent the actual peaks you see.
That's right. It's a visual way to build up the complex multiplets step by step, accounting for different J values.
Okay, that handles complex carbon-hydrogen neighbors.
Yeah.
What about hydrogens on oxygen or nitrogen? like alcohols, OH, or amines, NH. Do they couple?
Generally, no. Hydrogens on O or N usually appear as broad, unsplit peaks, fat singlets, as the source calls them.
Fat singlets. Why don't they couple, even if there are hydrogens on the adjacent carbon?
It's because of something called chemical exchange. These OH and NH protons are usually acidic enough or basic enough that they can rapidly exchange with each other, or with trace amounts of water or acid-base catalyst in the sample.
They jump on and off the oxygen or nitrogen.
Exactly. Deprotonate, reprotonate very quickly. The NMR experiment is relatively slow compared to this rapid exchange. So, from the NMR's perspective, the neighboring CH protons don't see a consistent spin state on the OH or NH long enough to establish coupling. The signal gets averaged out and the coupling disappears.
Huh. So if you see a broad singlet, how do you confirm it's actually an alcohol or amine hydrogen?
There's a neat trick. The D2O shake. D2O is heavy water made with deuterium instead of regular hydrogen.
Deuterium, the isotope?
Right. If you add a drop of D2O to your NMR sample and shake it, the exchangeable OH or NH protons will swap places with the deuterium atoms, D, and deuterium doesn't show up in a proton 1H NMR spectrum.
Ah, so the original OH or NH peak just vanishes.
Precisely. If the peak disappears after adding D2O, it confirms it was an exchangeable proton, like from an alcohol or amine. Very handy diagnostic test.
Okay, we spent a lot of time on proton NMR 1H. What about carbon? Carbon-13 NMR, is it similar?
It is similar in principle, but as the source says, it's often simpler in practice. Yay.
Simpler. How so? What are the main differences?
Well, first off, sensitivity. 13C NMR is much less sensitive than 1H NMR.
Why is that?
Two reasons. The main one is natural abundance. Only about 1.1% of carbon atoms are the NMR active 13C isotope. Most carbon is 12C, which is NMR inactive. Also, the 13C nucleus itself just inherently gives a weaker signal, so you usually need more sample or longer experiment times, or both.
Okay, less sensitive. What else is different? Integration. Coupling.
Generally, you don't get useful integration in a standard 13C spectrum.
Yeah.
The peak heights aren't reliably proportional to the number of carbons, and you also usually don't see coupling. Carbon coupling is very rare because the chance of two 13C atoms being neighbors is tiny, 1.1% times 1.1%.
What about coupling between carbon and hydrogen? That must happen, right?
It does happen, but usually the experiment is run in a proton decoupled mode. This uses a second radio frequency to constantly flip the spins of all the protons.
Yeah, I do that.
It collapses all the CH splitting, so each carbon signal appears as just a single line, a singlet. This simplifies the spectrum dramatically and also boosts the signal intensity, which helps overcome the sensitivity issue.
So 13C spectra are usually just a bunch of singlets. What good is that?
The main thing it tells you is the number of different kinds of carbons in the molecule. Each unique carbon environment gives one peak, so you just count the peaks. And just like in proton NMR, the chemical shift of each carbon peak tells you about its electronic environment.
Is the chemical shift range the same as for protons?
Yeah.
0 to 15 ppm?
No, it's much wider for carbon, typically 0 to over 200 ppm. Again, low ppm means shielded, high ppm means de-shielded. Carbonyl carbons, like in ketones or aldehydes, often show up way down near 200 ppm.
And you run the 1H and 13C experiments separately.
Yes, completely separately. The 1H NMR is blind to carbons, and the 13C NMR is blind to protons, unless you're specifically looking for CH coupling. They provide complementary information.
Okay, so we've covered a lot of ground. Chemical shift, integration, coupling, 13C. How did this all come together for someone trying to solve a structure?
It really is like assembling clues. You use that checklist from the source. First, chemical shift, the O value in ppm. Where is the peak? What does that tell you about the functional groups nearby? The electron density, that's your environment clue.
Okay, location tells you environment.
Second, integration for 1H NMR. What's the area under the peak? That tells you the relative number of hydrogens in that specific environment. That's your counting clue.
Your relative count, got it.
Third, coupling, the splitting pattern, using n+1. Who are the neighbors? How many equivalent hydrogens are on the adjacent carbons? That's your connectivity clue. Remember the complexities for non-equivalent neighbors and those fat singlets for OH-NH.
Connectivity map, check.
And fourth, the coupling constant, the J value in Hertz. What's the distance between the split peaks? Hydrogens coupled to each other must have the same J value. That confirms the
It's
connectivity.
confirming that. Right.
You put all those pieces together, environment, count, connectivity, conformation, and you can usually deduce the exact structure of the molecule. It's incredibly powerful.
It really sounds like it. But this technology, it's not just for chemists and white coats, is it?
Right.
It actually impacts everyday life.
Oh, massively. Especially in medicine.
You're talking about MRI.
Exactly. Magnetic resonance imaging. MRI machines are basically just huge, specially designed NMR spectrometers.
Huge is right. But instead of a small NMR tube
You are the sample. The patient goes inside the magnet.
and the name, wasn't it originally called nuclear magnetic resonance imaging?
It was, but interestingly, the nuclear part apparently made patients nervous. They associated it with, nuclear radiation or something dangerous, even though it just refers to the atomic nucleus.
So they dropped the nuclear to make it sound less scary.
Seems so. Just magnetic resonance imaging sounds much more benign. It's fascinating how the same fundamental physics applies, though.
So what does MRI actually show doctors? How does it work on a person?
It primarily maps the distribution and density of hydrogen atoms, mostly in water and fat molecules within different tissues in the body.
Different tissues have different amounts of water.
Exactly. Normal brain tissue, for example, has a different water content, a different hydrogen density than, say, tumor tissue, or bone versus muscle. By detecting these differences in hydrogen density and how the hydrogen nuclei relax back after the radio wave pulse, the machine can create incredibly detailed 3D maps of organs and tissues.
Allowing doctors to see abnormality.
Precisely. Things like tumors, internal bleeding, nerve damage, bone or joint injuries, things that might be invisible on a standard X-ray. It's an invaluable diagnostic tool.
So valuable it won a Nobel Prize.
It did indeed. Paul Lauterbur and Peter Mansfield won the Nobel Prize in Physiology or Medicine in 2003 for their pioneering work in developing MRI.
Wow. Okay, so that really brings us full circle. From figuring out tiny molecules in a flask to imaging the human body. That pretty much wraps up our deep dive into the amazing world of NMR spectroscopy. It's incredible how these fundamental principles have such broad applications.
Absolutely. We hope walking through chemical shifts, integration, coupling, and all the physics behind it has given you a more intuitive feel for how powerful this technique really is. Maybe sparked a few aha moments.
Well, thank you for joining us on this deep dive, exploring why NMR matters and how it works. Keep that curiosity going.
Definitely. Until next time, keep exploring, keep learning, and keep asking those important questions.